Okay, so welcome. So as Shitabra mentioned, I'll be covering the basics of complex networks. Those of you who have attended some of our previous workshops might find some of this material bit familiar, but don't worry, we will get to some new stuff which hopefully you've not seen. But I wanted to begin by since we have a very diverse sort of group of people, I wanted to begin with just the fundamentals and hopefully bring everybody up to the same level. So yes, as I said, on Tuesday I will be giving two talks where I will be going over a case study where we have data from a real connectome, and using some of these tools from network science, as well as some further ones that I'll discuss, we will see how we can extract useful information that can tell us something just by looking at the structure alone, right? So okay, so that's the plan of action. So to begin with, yeah, to begin with, I just wanted to zoom out and look at the big picture before we start getting into the details of what a network is and so on. This question is something which might seem a little bit vague, but trust me, it actually is something that is important, which is that how close are representations to reality, right? Some of you may have seen this famous painting by René Magritte. Is anyone familiar with this painting? So basically, it says, translated, "This is not a pipe," right? Which on the face of it sounds absurd, right? But it's a fact, because it's not a pipe, it's a representation of a pipe, or a picture of a pipe, or however you want to call it. And this just draws attention to the fact that when we sort of look at the world around us, sometimes we ourselves might get a little bit confused as to what the distinction between representation and reality is, right? I mean, once you state it, it's very obvious. But suppose I say, "Is this a pipe?" You will say, "Yes, it is," but it's not. It's not, right? And in a very similar sort of vein, there is this very amusing anecdote from Lewis Carroll from his book Sylvie and Bruno Concluded, where there's a discussion between a pair of characters, one of whom is basically talking about the largest map that he would consider to be useful, right? And he says that 6 inches to the mile is not useful enough. So he said, we tried having 6 yards to a mile, right? And then 100 yards to a mile, and then we finally decided that the best thing we can do is to have a map of the country on the scale of a mile to a mile, right? So basically, the map is as big as the entire country, right? And he says that, has it been used much? No, it's not. It's never been spread out yet. But I assure you, it does almost as well as using the country as the map. It does as well as having this map. So you don't even need the map, basically. So basically, I mean, this sort of this anecdote basically just drives home the fact that if you want to have a perfect representation of reality, you just need reality itself. And so any representation that we have is going to basically distill certain elements of reality which we find useful, right? So they cannot be a substitute for reality, but maybe they can in some aspects. And so that's basically where we come in with network science. So before getting into that further, I wanted to just show you this, right? So this is obviously a representation of reality, as we were just talking about representation. This is another representation, right? So what does this show? This is from actually quite an old map from 1908, and it shows various train lines from the London Underground, right? And you can see that the different, so this whole thing is a map, first of all, and overlaid on top of the map are various stations, and in these colored lines correspond to the different lines which you can see over here, right? So these are other different lines that you can take. Now, this was quite useful. I mean, it's always useful to have this information to know, like, well, which station do I need to get on to go to which other station, so which line do I need to take? Well, this is all very useful information, right? But then one can also ask the question, for the purposes of using the train, do I need all of this information? Probably not, right? So can anyone just say what information do you need? Suppose you're taking a train over here somewhere, or one of these stops, and you need to go somewhere else. What's the information that you need? You need the start and the end. Okay, that's one thing. You need the changes in between. Yes.
And we just need to know which railway lines actually go from start.
Yes. Yeah, just a few things like this. That's basically all you need to know, right? And
the shape of the line is not.
The shape of the line is not needed. All these other details are not needed. I mean, it might be a bit useful sometimes, but for most purposes, it's not so useful. You know, okay, fine. I'm going from here. I go to here, and so with that, this way. So with that thought, Harry Beck in 1933 came up with an alternative form of the map, which actually became so famous that this similar sort of design is still used today. Right? You probably, most of you who have been on a metro have probably seen a map that looks something like this. Basically, you just have these sort of colored lines. You have a few sort of like dots or squares that give you the names, and you know like where you need to change over. That's it, and it gives you a rough idea about north to south, but it's not very accurate. It's just say, okay, wait, go roughly north, and so on. Mostly the orientations are based on trying to accommodate all the information. That's about it, and this works perfectly, right? So this is just to drive home the point that you can have representations of reality which can provide you very useful information while discarding a lot of details which might not be relevant for the question that you're asking, right? So this is a good sort of point to step off to start talking about what a network is. And for me, I think this is possibly the best way to think about networks in general, right? You can think of networks as an abstraction of reality, or a specific kind of abstraction of reality, wherein you have some objects, could be anything depending on what it is that you're interested in, some objects, and they could have similar properties, they could have different properties. All of that, we're not saying anything about it. We're just saying that there are these objects, and these objects have some relations between them, right? So, and they could have a single relationship, they could have multiple relationships. The relationships could be directional. It could be that one object has some influence on the other. Like, for example, if you're talking about lineage, so you can have parents to children. It's not a two-way link, right? So you can say I am the parent of so on, right? And the links could have different properties as well, right? The links could be maybe the one link could represent who are my friends, one link could represent my family, and so on, right? And also the other thing is that the link might not necessarily correspond to something which necessarily has a physical interpretation. It could be something that is a derived quantity. You could say that, well, maybe if you look at the properties of these objects over time, there could be some correlation in their behavior, and this correlation can be captured as a link. So it could even be something like that. Right? So this way of looking at networks actually gives you a very nice starting point to think about it, because then you understand that whenever you're presented with a network, it is a kind of abstraction of reality. So it's not going to tell you everything, but the things that it does tell you are going to depend very strongly on what the objects are, what the relationships are, and how exactly they are different. Right? So, and also another point that I forgot to mention is that the network can change over time as well. That's the other thing. The networks need not necessarily be completely static, right? Because you could have, if it was completely static, then there's no life basically, right? The things are bound to change over time in general, right? Yes. So with that, So with that, we focus. So we turn our focus to the brain, right? which is the subject of this course, right? And we're going to look, in reality, as you heard in the first talk, there are a huge number of neurons in the brain. There's like about 10 to the 9, I think it was, over to 10 to the 9. It's in the order of billions, and 1,000 times more links between them, right? So if you were to have a complete network of the entire brain, it would be sort of unfeasible to sort of know how to extract information from it. You could in principle. I'm not saying that it's not possible, but it poses some challenges, right? And actually that's going to be the subject of the next lecture that I will give on Tuesday, right? So basically, you have the brain, and you know what the various connections are. How do you start to extract information from it, right? So yeah, so that is going to be basically the target of these set of lectures. But before that, we have to go back to the beginning, right? The beginning of network science, which is this problem, which some of you might have heard of. How many of you know this problem? Just be honest, please. Yeah. Wow. Okay. So a lot of you have heard of this problem. Okay. Those of you who don't know this problem, yes. Yes.
It looks like the flow of information is unidirectional. The context area at least.
What does the color represent in this case?
Here, okay, so this is obtained from DTI imaging. The color mapping, I think it's arbitrary. I don't remember what was done in this study over here. But there will be some lectures on DTI most likely next week. So so this is done through by tracking, like the water, that's sort of the movement of water and so on. So the details will be covered in that class. Okay? Yeah, and in general there will be direction also. That of course that is true. Okay. Okay. So those of you who don't know about the problem, so those of you who don't know, just be silent for the sake of those who don't. This is a very famous problem that was from the 1700s, and the problem is it's seemingly very simple, but it's a little tricky. Right? So essentially, this is the city of Königsberg, and you can see there's a river passing through the city, and a number of bridges, and the bridges have been sort of circled over here. Now, suppose you have a visitor to this city, as somewhere, it could be anywhere. The visitor has come to the city and says, okay, I want to travel across all the bridges passing over the rivers, right? But I don't want to pass over any bridge twice. Okay? How does the traveler do that? So those of you who don't know about this, can you, anyone would like to guess what would be the way that the traveler could achieve this? Okay. Okay. Let me make this easy. Okay. So let's assume that the traveler is over here, right? So what are the options? The traveler can go here, and can go here, right? These are the three options, right? So let's assume that the traveler goes here, right? So can anyone sort of guess what would be like a path that could be taken? Anyone wants to volunteer? Okay, since you're keeping very quiet, okay. Let me just pose a hypothetical path. Okay, so let me say it goes like this, like this, like this, like this, like this, like this. Okay, so I finished these 4 bridges, and now I'm going to come here, and I finished. There's just 2 bridges to go. So I could go here, or I could go here. There's a problem. Suppose I go here, then these bridges have all been traversed, and I can't go back as well. So I'm stuck. Suppose I go here, then these bridges have been traversed. So I'm stuck again, right? And it can be shown that no matter where you start, suppose I started in here instead, or suppose I started, it doesn't matter. I'm not going to be able to do it. And in order to figure out why you can't, there's a simple sort of exercise that I like you to try out, right? So if try and draw these patterns without taking your pen off the paper. You have all had notebooks. Try and draw this pattern without taking your pen off the paper, A, and B, without crossing any path twice. Okay. Now tell me which of these you can do and which of these you can't. I'll give you just half a minute because I don't want to wait for too long. Hopefully you're all doing it right now, okay? And you need to tell me if you've done it or not. Okay. Hopefully, what about this one? Have you been able to do it? All right, cool. What about this one? Yes? Okay. What about this one? No? Okay. This one? Okay. Does anyone know why you can't do it over here? Sorry?
It's on.
Well, I mean, so you're on the right track. So basically, so this was the solution that was proposed by Euler back in 1736. So he says, okay, fine. So I have this map, right? But well, I want to make the problem very simple. Let me make an even simpler abstraction of reality. So let me just draw this sort of situation in terms of a simple graph, right? So these green circles correspond to the various banks. So there's one bank here, and so on. Basically, I've marked A as one bank, B is, and so on, right? And the lines correspond to the bridges that exist between these banks, right? And you can see that, like suppose I go from B to A, and then I'm back at B, B to C, I'm back at B, and then I can leave B, right? But now with the D, I'm stuck. I can't go back to A. I can't go back to C, right? So from this, he could very quickly figure out that only terminal vertices can have an odd number of links, right? And so, but you can see here all the nodes have an odd number of links. This one has an odd number. This one has an odd number. So we have 5, 3, 3, 3, and so on. So if you had only two of them with an odd number of links, no problem, right? But so he showed through a very simple sort of graph, he solved the problem, right? And this is was very influential because this is what gave birth to the science of graph theory, right? So people talk about networks sometimes, graphs sometimes, but actually they're sort of one and the same. I mean, network science sort of took off in the 90s and early 2000s. There was a renaissance in this field, but essentially they're sort of more or less the same thing. But a network of connection between entities can be analyzed by viewing it as a graph. That's about it, basically. Or in other words, a network is a graph where the objects and relations of the graph can be mapped to some real world setting. The graph is just basically the structure, the underlying mathematical sort of framework that you're working with, and the network is what you're describing in reality. I mean, that's a simple way to talk about it. I mean, I could even call this a network. Sorry, I could even call this a network, and I wouldn't be wrong. I mean, the terminology is a little bit. I mean, there's no sort of hard and fast way of thing, but this is just the general convention, right? So okay, so that is what it is, and so. Now I will briefly go over some basic concepts in in graph theory very quickly. These are very elementary, so I'll try and rush through them, and hopefully. And so, by the way, we'll be putting up the slides for as many lectures as possible on online. I'll be putting up mine. So if you would like to refer to this later, it will be on the website. Okay. So yeah, and of course, if you have any questions later, you can feel free to ask me. So the most basic concept is, as I said, a network can be viewed as a mapping between objects and relations. So the objects are what we call nodes or vertices, The relationships are what we call links or sometimes edges, right? And the degree of a node, right, is essentially the total number of links that are associated with it, right? So for example, for this little graph, we see that node 1 has degree 1, 2 has degree 3, and so on, right? So that's what we refer to that, right? So for example, and again here, so this node has a degree 1, 2, and so on, right? This is just very basic stuff. Yeah, did I skip over one? Oh yeah, I did, sorry. Yeah, and graphs can also be directed, right? So as I mentioned, for some types of networks, it doesn't make sense to have links going in both ways, right? So depending on what you're talking about, right? Or what it is that you're studying. As I gave the example of a family tree. Family trees have links going only in one way, right? So such graphs are called directed graphs, right? And in those type of graphs, you have to talk about the connections that are incoming separately from the connections that are outgoing, right? And so for that we call them the in degree and the out degree, right? So for this network you have a separate in degree, a separate out degree, and the total degree is just the sum of the total, right? So that's what it is. So basically for a network like this, you have one in degree, the in degree is 1, out degree is 1, the total degree is 2, right? That's it. You can also, as I mentioned, have weights to your links, right? So depending on what it is that your relationship is, the link might not necessarily be the same between different nodes, right? You could have stronger connections or stronger links between some nodes, weaker links between others, right? And when you're using that information, such networks are called weighted graphs, right? And so essentially all you do is for every link. So here the links have been numbered over here, and or the edges have been numbered, and these are the corresponding weights. In this example, I've just indicated the weight by the thickness, but that's basically what it is. I mean, you can have different instances of this in different types of networks. So this is what is known as a weighted graph. All right. Now there are some other types of graphs which I'm sure many of you have at least heard of them, if not studied them. But as I mentioned, not all types of graphs could have the same. Not all the links between the objects in the graph could be the same, right? So you could be describing a situation where you have a bunch of objects wherein there are multiple relationships between them, right? So you could have, for example, these 5 objects. This could be one type of relationship. As I mentioned, these could be, let's just say these are 5 individuals, and these are this is the friendship network, you could say, and this could be maybe the network of people who they meet on the bus going home, and this could be the network of people who it could be something else. Anyway, but the point is, it's the same objects could have multiple relationships between them, and such graphs are called multiplex graphs. Okay? So basically, the same nodes but different relationships between them. You could also have bipartite graphs, wherein essentially you're only talking about links between different classes of objects, right? So for example, here you see that you have a bunch of objects 1, 2, 3, 4, 5, and another bunch of objects A, B, C, D, E, right? This could be, for example, like these are 5 individuals, and these are 5 films that they have seen, right? So these could be the different films. So basically, the one has seen film B, and so has 3, and so on. It could be something like this, right? So suppose you have 2 different classes of objects in your network, and you need to classify the links between the links pertaining to the relationship between these 2 object classes. Such graphs are called bipartite graphs. Okay. Hopefully, so far this is all very basic stuff. So hopefully this is. Okay. Now we start to look at how we represent these things mathematically. Okay. So thus far we've been dealing with very small networks in all these examples, so it's very easy to just look at it and see what's going on, right? But this is not so straightforward if you have hundreds of nodes, thousands of connections, and so on. I mean, you just cannot look at it and see what's going on. You need to have a way to deal with this mathematically, right? And so for this purpose, one uses this structure which is called the adjacency matrix. The adjacency matrix is something that basically specifies all the connections in the graph. So suppose I have two nodes I and j that have a connection between them, then we specify aij is 1 or else it's 0. It's very simple. Is there a link between I and j? Yes, put a 1. No, put a 0. Okay? So that is your adjacency matrix, just the presence or the absence of a link. And I don't recall if I have it in a subsequent slide, but you could also have, in the case of a weighted graph, the number could correspond to the weight, right? So suppose you say, okay, suppose have nodes I and j, they have a connection between them. What is the weight of that connection? I can specify that number. So then that's that is the matrix of connections of that weighted graph. But anyway, that's just an aside. So as I said, so one can define the adjacency matrix. One can also define the matrix for a directed graph, right? So if you notice in the case of of an undirected graph, you can see it's symmetric, right? So if you look at this matrix over here, along the, if you go look along the diagonal, it's flipped, right? But in a network like this, it's not, clearly, right? Because a link from 1 to 2 does not necessarily mean a link from 2 to 1, right? So that's what the matrix would look like in this case. And finally, when you have an adjacency matrix, now it becomes very easy to find the degree, right? Because I don't have to go and count the number of links manually. I just have my matrix and just say, all right, so what is the degree or the total number of links that are there that correspond to node I? I just take the sum across the node, right? So across the links of that node. So basically, just for example, look at this matrix over here. I will say that okay. So yes, sorry. This is another point I want to mention. So how do you actually sort of obtain a matrix for the case when it's undirected? It's going to be a little different for the case when it's when it's directed, because when it's undirected, it doesn't really matter what's along the rows or the columns. It's the same thing, right? Because essentially a link from 1 to 2 is the same as a link from 2 to 1. But it's not the case over here. And so now it matters which one is your source and which one is your target, right? So one convention to use, and this is definitely not the only convention, is that people tend to use the rows to correspond to the source and the columns to correspond to the target, okay? But I have to point out that this is going to differ from field to field, right? So some fields they use this convention, and some other fields they use a different convention. So it is preferable when you yourself are using such matrices to not just assume the convention and to state it explicitly. It's just helpful for your audience, just to state that we have specified this adjacency matrix where let's say the rows correspond to the source and the columns correspond to the target. It's just helpful, right? Right? Okay, so this part's clear, right? So basically, so remember, when it's directed, it matters which ones are the rows and which ones are the columns. So getting back to what I said about the degree, right? So suppose you have a matrix, and let's just say you have this matrix over here, right? So I want to find the degree of node number 2. All I have to do is I just have to take the sum along this row, right? So then I see that sum is 3. There are 3 links, right? So that's just expressed over here, right? And so similarly for the directed graph, whether I take the sum either along the row or the column, depending on whether I want the in degree or the out degree. That's what I have to do, right? So yeah, so that becomes very easy to deal with. Cool. Another point that I just want to briefly mention, this is just a definition, right? So there's nothing too deep over here. These are just some terms that you tend to hear. Sometimes people talk about dense networks, or people talk about sparse, or the density or the sparsity of a network. What does that basically mean? So suppose you have a graph like this, right? And so you see that there are a lot of connections between the various nodes, and this is what the agency matrix is going to look like, right? So from this you can see that the of all the node pairs that can possibly exist, most of them do, or many of them do, and so in this case, the network is said to be dense. Now, this is a very subjective sort of term, right? So there is no like cutoff beyond which people say, okay, beyond this it's dense, or below this it's sparse. This is just people use it more colloquially, but when people say it is, I'm increasing the density, basically it means that I'm approaching the limit where where basically all node pairs that can exist do exist, right? And similarly, for the case of a sparse network, suppose most of the links which can exist are actually absent, then we say that, well, it's sparse. Again, what is most? That is something which is it's not very clearly defined, but you get the general idea. Is it closer towards one limit or closer towards the other limit? So this is just for your information, so that you know what these terms mean, right? Okay, now walks and paths. Okay, suppose I have a network, right? And I want to talk about how far apart two nodes are. Now I'm not talking about far apart in terms of physical distance. I'm talking about far apart in terms of the network topology, right? You can talk about it in a couple of ways. You can talk about it in terms of, for example, what's called a walk, right? So a walk is basically a route along the edges of the graph, and if you have an undirected graph, you can cross it in either direction. So for example, here this is a walk, okay, basically going from here to here to here to here to here and so on, right? That's all a walk means. A walk basically means that I'm traversing the links of the network, and the length is basically just the number of hops I take along the way. So here I have taken 5 hops to go from here to here, right, along this particular walk. And a path is a self-avoiding walk in which you don't traverse any edge twice. So this is not a path because I've traversed this edge twice, right? Suppose I had just gone from here to here to here, then it's a path because I've not crossed any link twice. So this is another path like this, right? So basically going from one here to here to here, this is a path. So this is just so that you're clear between the difference between when people talk about walks versus talk about paths. You can have walks going back and forth in the same link. You cannot do that for a path, right? So okay, yes. Pardon? Yes. I don't think I don't think walk is
in the length for a weighted graph. The length will be the sum of all the weights of all the vertices taken, or would it still be the number of hops?
So I think it depends on the context. I mean, if you're only just interested in terms of like the distance, then it doesn't matter. See, it also depends on what the link corresponds to. If the link corresponds to some process wherein it's sort of it corresponds to how easy it is for something to flow from one node to another, then you have to take that into account. But all of that information is not considered over here. This information is purely just talking about graph distance, right? So, but yeah, so there you have to consider things like dynamics and so on, which I haven't got into this stage. So okay, so if that's what the path is, then the shortest path length. So you can have multiple paths. So between, let's just say between 1 and 3, I can have multiple paths. I can go from like 1 to 2 to 4 to 3. I can go from 1 to 2 to 5 to 3, 1 to 4, 5. So they can go have multiple paths, right? But the shortest path length is just that. It's the shortest of the possible paths that can exist between a pair of nodes. So for example, in this graph over here, if I look at all these node pairs, these are the shortest paths. So between 1 and 2, of course, the shortest path is 1, obviously. Between 1 and 3, I mean, clearly it's 3, right? Because I can go 1, 2, 4, 5, 3, but this is the shortest. I can't go less than 3, right? And so on. One can figure out the rest for the other ones as well. And suppose I do this for the entire graph, then I can. Oh, sorry. Yes.
So in the previous slide, you defined the path to be where no two edges are repeated, right? Isn't it supposed to be vertices? It's a stronger condition for path. typically in graph theory?
No two vertices are well. I mean, it will happen. The same thing should happen, right? I mean, so even here, this is a path. So you're not going to repeat the vertex, right? I mean, the only way you're going to repeat the vertex if, well, I suppose.
There are 4 edges along.
Okay, right. Yes. Okay, this does not preclude that. This definition does not preclude that, but I guess that's still all right. I mean,
But you can have like a vertex prohibition is stronger than an edge prohibition, like repetition.
that's I agree. It's stronger. It's true. It is stronger, but you know, like okay, for the purposes of things like finding shortest path and so on, I guess that's by default is going to be ruled out, right? Because if you're going to come back to the same edge again, immediately it's not going to be valid for a shortest path. So yeah, it depends on the kind of problem that you're interested in. I mean, by itself, this is a valid definition. I mean, yeah, it's true that suppose you don't allow the same vertex to be repeated, that is a stronger condition. But yeah, it's not. It depends on what it is that you're trying to study. Okay. Yeah. So anyway, so finding out the shortest path length, you can of all the nodes, you can then define the diameter. So the diameter is basically, so knowing all of these, you just say what is the longest shortest path, right? So in this case, it's 3, right? So because you cannot have a shortest path which is longer than 3. So this is what is referred to as the diameter. So this, in some sense, gives you an idea of like you know you can say the span of the network, like how wide or how basically how what is the, I mean, because this is not, I mean, since this is not defined on or not necessarily defined on some sort of Euclidean space where you can have an idea regarding size, this diameter gives you a kind of a nice proxy for that, basically how wide or how far apart, because when you have physical processes that are occurring on the network, let's just say you have something that's diffusing and so on, then things like this become important because it kind of gives you an idea of like the time scales that are going to be involved and so on, right? Okay, so yeah, and then the average path length, right, is just the average of the shortest path lengths between every pair of nodes, right? So let's just say that now we have all of these. So remember, we can also have from 1 to 2. You can also go from 2 to 1 as well, right? So I mean, in principle, this Dij, it could be flipped as well. It could be D. I mean, so it could be D1 to 2 or D2 to 1. So suppose we write down all of this, and you just take the sum of all possible shortest paths. Then so in this example, you see that it's around 30, right? But having computed this, you can find what the average path length is by just dividing by the total possible paths that links that pairwise links that can exist, which is basically n square minus n, right? Because we're not allowing for self links. If it will only be n square, but since we're removing the self links, it's a minus n. So basically n times n minus 1. So you're scaling it by that. So that is what gives you the average path length. This is just a definition. There's nothing very complex here. Yes.
So in very large graphs, can you calculate path length algorithmically? What is the complexity of that?
So actually, I think I was just about to come to that in a couple of slides. Yeah, so you need to use things like this breadth first search algorithms. It is possible. It becomes a little bit difficult, but it is. I mean, so there are techniques like this that can be done. So I'll come to that in quickly. Which reminds me, I'm also running a little bit light, so on time. So I'll speed up a bit now. Okay, so up to this point, I think is fine, right? So okay, so I have also just included a bunch of questions in these slides. In the interest of time, I mean, I'm not going to work through all of these with you. Hopefully, you will do these yourself, okay? And maybe in the next class, if there's time, I'll ask some of you to give me the answers. But just these are very, very simple questions. They should not take any time. If you understand the concept, this is like very straightforward. But I have just included these just so that you get that practice, okay? Okay, so suppose you so suppose you have once again you have a graph like this, Now, suppose we just talk about walks of length 1. Okay, so the walks of length 1, we can see that between every pair of nodes, you can figure out. Okay, so between here and here, this is one walk of length 1. Between, let's say, 3 and 4, there's one walk of length 1. And you notice that this is basically just the same as the adjacency matrix. It's almost by definition, right? Because if you're only considering walks of length 1, that's basically just the links that exist, right? But if you talk about walks of length 2, then you can have more. Like for example, between, let's say, 2 and 3, you can have one path like this. So that's 1, 2, a walk of length 2, and another one like this, right? So basically, between 2 and 3, you can have 2 walks of length 2, right? And you see along the diagonal, you now have some value. So what does it mean from 1 to 1? Well, basically, you're going from here 1 to 2, and then back to 1 again. And see, 2 to 2 is 3. What does that mean? I'm going from here back again, back again, back again, and so on. And so along the diagonal, you see that basically this is just the degree, right? So essentially, if you look at the matrix of the walks of length 2, along the diagonal, it just gives you the degree of the node, right? Basically going and coming back along each of the links, right? Yeah, so basically, so you can compute that. And a quick way to find the total number of walks, so because this can be done very easily in a small network, right? But suppose I had a large network, how do I do this? Well, this can actually be done by through a very simple trick. So suppose you do matrix multiplication, right? So basically, I have this matrix and the same matrix again, right? What's going to happen? So let's just consider this row and this column, okay? Row 2 and column 3, right? When I do the matrix multiplication, what's this going to give me? It's going to give me a 2, right? So what does that correspond to? Basically, it's like all the nodes of distance 1 from node 2, that's this, right? All the nodes of distance 1 from node 2, and all the nodes of distance 3 from node 1, that's this. So that is going to give me the intermediaries. Basically, I go from 2 to something and then that to 3. So that gives me the paths of length 2 between 2 and 3. And suppose I do the full matrix multiplication, that gives me everything. It gives me all the paths of length 2 between every pair of nodes. Now you can see that this gives you a very simple sort of way to figure out all paths of length d by just simply multiplying the matrix with itself again and again, right? So this is A is the adjacent matrix. You keep multiplying with itself again and again. You can get all the paths of length d between every pair of nodes. Right? So this is just a neat little trick which is quite useful for when you have large networks. You can immediately figure out these paths. Okay. And as I was mentioning, suppose now you have a large network and you want to figure out the shortest path between a pair of nodes I comma j. There is a way to do this, right? So this algorithm is a very simple algorithm, but it's very powerful. It's called the breadth first search algorithm. So you start with a node, right? And for simplicity, I'm just going to color them with a certain convention that the node I'm considering is going to be green. The neighbors of this node are going to be blue, and the remaining nodes are something else. Okay, so first I'm going to find the neighbors of the green node. Okay, so these blue nodes are distance 1 from my green node. Okay, then what I'm going to do is I'm going to discard the green node and then I'm going to color these green. Right, so these are the nodes I'm not going to consider. For each one of these nodes, I'm going to find the neighbors. Right, so basically, you see 6 is a neighbor of 3 and 1, and 4 is a neighbor of 5. Right, so and 8 has no neighbors, but these 3 are neighbors of these nodes. So these are now distance of 2 from 7. You can see that, right, because these are distance 1 from the green nodes, and the green nodes are at distance 1 from 7. Right? And then I do it again. So now I discard these green nodes and I color these green and say, okay, fine, what are the neighbors of these nodes? Well, there's 2. So 2 is of distance 3 from node 7, and so on. Right? This can be a little bit of a cumbersome algorithm, especially if you want to find out like all the possible shortest paths in a very large network, but it does the job. Right? This is just to give you an idea about some of the techniques that people try to use to figure this out. Okay, since I don't have a lot, how much slides do I have? Okay, fine. Maybe I'll just finish as much as I can, and then I'll continue it the next time. So, okay, the other thing that I wanted to talk about is, okay, suppose you, okay, very often in networks, when you have nodes who that have links with each other, right? Then it can happen that the links the neighbors who they form links with could also have like, okay, I'm saying it badly. So nodes that form links with one another. Okay, so you have two nodes, and so they form links with each other. It tends to happen that they also form links with those who are the neighbors of the ones they're forming links with. So okay, let me give you an example. Suppose I become a friend with somebody, right? It's likely that I'm also friends with the person who that person is friend with, right? That's how things tend to work, right? It's very, very unlikely that I'll only be friend with this person, but not be friend with any of his friends. Right? Just an example. So that's something which one can measure in the network using what's called the clustering coefficient, right? So the clustering coefficient, there are two types of clustering coefficient which people typically talk about, what's called the global and the local clustering coefficient. So I'll first mention the global clustering coefficient. So the global clustering coefficient is defined as follows. So first of all, what you do is you consider triangles of nodes. So in a triangle of nodes is basically something like this, right? So basically you have your 2, 4 and 5, they form a closed triangle, right? And you notice that this triangle contains 3 closed paths, right? Basically you have 2 to 4, 4 to 5, 5 to 2, right? Then 4 to 5, 5 to 2, 2 to 4, and then 5 to 2, 2 to 4 and 4 to 5. And because this is an undirected network, it doesn't matter. Basically the point is you have 3 closed paths, right? And you also look at what are called connected triples, okay? So a connected triple is basically, so suppose I have nodes A, B and C, and both A and B have a link, A and C have a link to B, then it's called a connected triple, right? So for example here you see 2, 5 and 3 are a connected triple, and 1, 2 and 5 are a connected triple, and so on. Basically it just means that the central node is connected by the 2 other nodes. So just as an example, suppose let's just say I remove the 1 and remove the 3, I just have 2, 4, 5, okay, I just have this triangle. Then you notice that the C is going to be basically number of triangles times 3, because there are 3 closed paths, divided by the number of connected triples, which is in this case you see that I have 2, 4, 5 is one connected triple, 4, 5, 2 is a connected triple, and then 5, 4, 5 to 4 is another connected triple, basically. So if you look at this form, so then the clustering coefficient is just 1 here. If you just have a perfectly closed triangle, suppose I had 2, 5, 3, then I don't have a triangle. I just have so it's going to be 0, right? Because I have a connected triple, but I don't have a triangle. Anyhow, so the point is you compute this over the entire graph, and then this is what gives you the global clustering coefficient. Okay, so it tells you that on the whole network, how likely are nodes who are connected to somebody likely to be connected to the nodes they are connected to. Okay. If this is a little bit tricky to how to get your head around, maybe this will be a bit easier, which is the local clustering coefficient. Okay, so the local clustering coefficient is something like this. Okay, so suppose you have let's just look at this example over here. Okay, so I have this node connected to 3 nodes. Now the question is, amongst these 3 nodes, how many links exist, right? So I put a question mark because I'm saying, okay, this is what we need to calculate, right? So you know that in general there can be 3 links. I mean, sorry, in general, yeah, at max there can be 3 links, but of those 3, how many actually exist? And that's basically what it is. So it's the fraction of these links that actually exist. The fraction of potential links that could exist divided by those the fraction of links that do exist divided by those that could exist. That's what it is. So okay, so hopefully that part is clear. So basically you're just looking at you're just trying to figure out the nodes that can exist divided by nodes that that do exist by those that can exist, right? Again, so if that is cleared, actually maybe just to drive home the point, I can sort of talk about this example up here. So in this case, what's the clustering coefficient of this blue node over here? Sorry? So this node has two neighbors, right? Right? And how many links can exist between these two neighbors? One, but there's no link between them. So that's that immediately tells you that's the clustering coefficient. And in this case over here, you see that I have 1, 2, 3 neighbors, right? And I have 2 links between them. But in principle, I could have also had that third link, right? So then that gives me 2 by 3, right? And you can work out the same for this one as well, right? So again, the slides will be online, so I strongly urge you to try this out. And these are some. This is cool because this is now, if you consider like a lattice with different types of geometry, one now notices that in these lattices, all the nodes are going to have the same clustering coefficient, right? Because essentially the neighborhood for every node is going to be similar in structure to that of everybody else. So everyone's going to have the same clustering coefficient. But the question is, what is the clustering coefficient? So that's what I would like you to calculate. Okay, straightforward. Okay, I have a few minutes to go. Okay, I will finish with components and then I'll stop. I still have to cover random networks. Maybe I'll cover random networks in my next lecture and then go on to the main part of the talk, which is on modularity. So I'll just talk about components and then I'll stop. So okay, the last thing I want to talk about today is the fact that some types of networks. In some networks, you might find that you might not have a path that exists from every node to every other node. So for example, here I find that between 1, 2, 3, 4, there's some path that exists. I can always go from 1 to 21 of these other nodes, and similarly, so I can always traverse these links to reach the other nodes amongst 1, 2, 3, 4, and similarly 5, 6, 7, 8. But I cannot go from here to here. It's not possible, right? We say that a pair of nodes are connected if there exists a path between them. So 1 and 3 is connected, 1 and 5 is not connected, right? And a component is a subset of the network where all the nodes are connected. Okay, so for example, here, this is just basically the same network, right? So the red and the blue form 2 components. So in the red component, all the nodes are connected. In the blue component, nodes are connected, but these are separate components, right? And when people talk about bridges, well, basically, suppose hypothetically I had a link between 4 and 5, right? Then the presence or the absence of that link would make the network disconnected. So that's what when people talk about bridges, that's basically what they mean. It means that the presence of this link is essential to stop the link from splitting into further components. Okay. So anyway, so suppose, okay, so with that definition of components, I also just want to just mention a few more definitions before I talk about my final. Actually, how many slides do I have beyond? Okay, I'll just. So in the case of directed networks, components becomes a little trickier now, because you see now you have to follow the path of the arrows, right? So you see here, suppose I consider this 6, 7, and 8. There's a path between all of them. I can go from 6 to 7 to 8. I can always, there exists a route between them. But to 5, there's a problem, because I can reach 5, but I can't go from 5 to any of the other nodes in this component. So this part is what's called a strongly connected component, right? So this you can find a path between any of the nodes within this component, but if you include 5, then it becomes a weakly connected component, which means that you can reach any of the nodes in this component, but you cannot necessarily starting from a node, you might not be able to reach the other nodes. Right? So that's what a weakly connected component is. So suppose you ignore the directed nature of the edge, then it becomes a connected component. Right? And similarly, the in and out component are basically, so suppose I have, let's say, a node 2, the out component is where can I reach from 2. So I can reach all these guys, right? I can't reach 1. But 1 is the in component of, because I can reach 2 from 1. So that's what the in and the out component is. Okay, so again, these are all just definitions. Okay, there's nothing very, very profound over here. So just so that you understand what these terms mean. Okay, the last thing I want to mention. Okay, so this I mentioned this last time. Somebody somehow guessed this. So in this case, I have shown an adjacency matrix, but in a different form. Usually I'm showing in terms of zeros and ones, right? But here I actually have hundreds of nodes. Okay, I have hundreds of nodes, and the white squares represent connections between the nodes. So you just imagine I have 1, 2, 3, 4, 5, 6, 7, up to some 150, 200 something over here, and similarly over here. It doesn't make sense to put all these numbers in there. So I'm just going to color them. Color the 1 as white and 0 as black. Okay, so then I get a figure like this. So another thing that I've done is I have made sure that this network has multiple connected components. Okay, so I generate this network in a way that there are some connected components wherein so you can go within them, but you cannot jump from one to another. There is no path between the connected components. But just looking at this, I want to just want to, how many connected components are there? Anyone has a guess? I'm looking at you, Harish. You got it right last time, yes. No, so okay, it doesn't make sense to me. The answer is actually 4, but that's not the point. The point is actually by looking at it, it doesn't make sense to find out the number of connected components. So how do you find the number of connected components? There's a way to do that. So to do that, what we do is we define what's called the graph Laplacian. Okay. So the graph Laplacian is defined as follows. Sorry. Suppose you have A, which is your adjacency matrix, and then you have D. And D is basically what's called the degree matrix, which basically contains the degree along the diagonal and zeros elsewhere. Okay, so that's just the definition of the degree matrix. It's just simply the degree of the nodes along the diagonal, right? So the graph Laplacian is how it's defined. L equals D minus A. Okay. So for a adjacency matrix like this is what the graph Laplacian is going to look like. Okay, so as you can see, it has the degree along the diagonal and then -1 and the other because of the minus A, right? So this is your graph Laplacian. Okay, fine. So now, but what do we do with this? Okay, so with this, it turns out something very fascinating can be done. Suppose you look at the eigenvalues of this matrix. So if you do that, then it turns out something very interesting, which is that the number of 0 eigenvalues of this Laplacian is going to indicate the number of connected components of the network. Okay. So let's just consider these two networks over here. Okay, so here are our networks. We know how to find the graph Laplacian. It's very simple. We find the graph Laplacian, that's LA and LB, right? And we take so here, by the way, I mean in this example, you can actually see the number of connected components. You can see that there are 2 components, so it's very obvious. So, but it's good because it allows us to kind of to validate our approach, right? So we take the eigenvalues and we see these are all our eigenvalues. And you see that this one has 1 0 eigenvalue. Lambda A has 1 0 eigenvalue. Lambda B has 2 0 eigenvalues. And sure enough, I mean that is the number of connected components. This one has 1 connected component. This one has 2 connected components. Right? Almost, it's fantastic. But you may, of course, be asking the question, well, why does it work? Okay, this is why it works. So suppose we again take our two Laplacians, and then we say so the Laplacian with a single component is going to bound to have an eigenvector which is just going to be something like this with all the ones and the eigenvalue 0. So what happens over here? So if this is 0, that means that all these entries are going to be 0. And then you multiply this by this, so what's going to happen? So basically, you're going to get plus, when I do the multiplication, I get +1 -1 0 -1. So the sum, basically take the sum of all that, the 0 0 0, and so then that's what it is. So that is satisfied, but this is satisfied by an eigenvector which has an eigenvalue of 0. And the same way over here, suppose I have an eigenvector of this form, it's going to be satisfied with an eigenvalue of 0. So if I take lambda 0 and then I just multiply this, then I say, okay, so all of these is 0 0 0 0, and then it works. And one can flip it around and get the other one as well. So basically, this is how it's a very, very simple way by which you can use the graph Laplacian to find the number of connected components in your network. Okay. So this is very straightforward. Hopefully this is clear, right? So this is a nice approach you can use. Okay, since I've overshot my time, I think I'll stop here. I will have a few more things to cover. I'll cover that in the next class, and then I'll go on to the stuff on the macaque network, where we actually start to study some the functional property, the connection between structure, function, and so on. But hopefully this is just giving you a basic intro, and I would like you to work on the maybe what I'll do is I'll just put up partial slides without the ones that follow, and put up the problems, and then put up the other ones later once I finish the talk. So with that, I thank you.